All right, here we go again for the B lecture of this second week of the course. So let's see. Let's see where we are. We introduced, regression analysis, the simple linear regression model in the A lecture. And so what I want to do in this B lecture is not introduce anything new, but elaborate on what we already discussed in the A lecture, which is something that I will often do in this course. That sometimes we'll take 2 steps ahead and then take 1 step back and then delve a little bit deeper into what are we doing and how does it actually work, because usually that's the best way to learn. So I want to elaborate on a couple of things that we discussed in the A lecture. I want to elaborate on OLS, so this idea of using ordinary least squares estimation to find the values for our coefficients and for our standard errors. I want to also elaborate on the t-test that we use to test the individual coefficients in our regression model, so the coefficients for our independent variables x. And I want to elaborate also on the model fit a little bit more, so the goodness of fit of our model, how well does it fit the data. And then I'm going to close off on, showing you that linear regression and what we sometimes call descriptive statistics, particularly the mean, have a very close relationship and actually are really just variations of the same thing, which is, I think, very, very good knowledge to have if you better want to understand what regression models actually do and what they don't do. So let's start out with talking about OLS estimation. So we talked about, if we have a hypothetical independent variable that we want to analyze and we want to know how it's related to a dependent variable that we want to analyze, then we will have individual data points, individual observations that score different combinations of values on x and y, and we will somehow want to find a line that captures the linear relationship between x and y, the regression line, where that line is determined by 2 things. The slope of the line, so how fast does it go up if on the y scale, if we go 1 step to the right on the x scale, and where does it meet where does it intersect with the y scale. So the B1 coefficient, the regression coefficient for our independent variable x, tells us the slope, how steep is this line, is it positive or negative, and how steep is it, and the constant or intercept, the B0 coefficient, tells us where this regression line meets with the y-axis. So this is the point where x, our independent variable, takes the value of 0. And we talked about that, if you want to have the best line that represents this relationship, we actually want to find the line that makes the difference between what our regression model predicts. So the prediction is basically represented by this regression line, and what we actually observe on a dependent variable. So those are these individual data points. That makes the difference between that, as small as possible, because then we have the best predictions. And these differences between what you observe on a dependent variable and what you predict based on our model, those are the residuals. So these are represented by these red lines that indicate the difference between what we observe and what we predict in our model. And of course, would be nice if you could just somehow minimize the sum of those residuals. But the problem is that the positive residuals and the negative residuals perfectly cancel out against each other, because that's exactly how the regression line is defined. It is that regression line that makes sure that the positive and the negative residuals perfectly cancel out, because then we have the line that gives us the best predictions. That makes that makes sure that our error, our residual, is as small as possible. So this is the same problem that we saw previously already when we talked about calculating the variance around a mean of a variable. That, we might just want to look at deviation scores relative to a mean, but the sum of deviation scores relative to a mean by definition is always 0, because that's exactly how the mean is defined. It's that value for which the sum of deviation scores is in fact 0. As a matter of fact, I told you that if we use the usual trick of getting rid of that problem by taking squares to calculate the variance, because that's what the variance really is. It's the average squared distance to the average and mean squared distance to the mean. Then basically the mean is that value that makes sure that the sum of deviation scores is equal to 0, And that also means that it is that value that makes sure that the sum of squared deviation scores is the smallest value it can possibly be, because that's exactly how the mean is defined. And that would be an alternative way of finding the right value for the mean, is somehow mathematically working out what is the mean value that will result in the smallest possible sum of squared deviation scores. And actually that's what ordinary least squares estimation does for a regression model. It works exactly by finding a regression line that minimizes the residual sum of squares. So the squared values of all these individual residuals added up together. That's exactly what it actually does. Yeah, minimizes finding mathematically the smallest value for that sum of squared residuals. That's what it actually does. Of course, you might ask, or probably you won't, but I will ask for you, how does that actually work? Because so far we've just let SPSS do it for us, and that's great. It's awesome that SPSS wants to do that for us. Yeah, it will be helpful in the long run during this course and also later if you actually know what is SPSS doing when it is figuring out the right values for the coefficients for you. So we're going to look a little bit under the hood as to what is actually happening. And we're going to do that for this simple linear regression model that we saw as the general shape of y I, so the observed value on the dependent variable for each case I, equals b0, the constant or intercept value, plus b1, the value of the regression coefficient for our independent variable x, multiplied by the value on our independent variable x for each individual case I, plus the residual error term that we have in the model that is also different values for different cases. So far I'm using the term error and residual interchangeably. For now it doesn't really matter whether we are talking about error or residual. They mean the same thing. They mean basically this is the part of the model that leads us to a prediction about what y should be, and the error or residual captures, well, what is then the difference between what our model predicts based on b0 and b1 and what we actually observe on a dependent variable. I remember these are probabilistic relationships that we're analyzing, so we don't expect that we are able to perfectly predict the outcome, so we have to allow some error in our model, some residual in our model, to actually get to the value of the outcome. Yeah, so basically we're taking the actual observed value on our dependent variable and chopping this into three pieces here: a constant plus the regression coefficient multiplied by the independent variable plus whatever is left. Those things added together give us the observed value. So for now I'll talk about residual and error as interchangeably. Later in the course we'll reflect a little bit more about what is the difference between when we talk about error and when we talk about residual. So the nice thing is the OLS estimation procedure actually boils down to a relatively straightforward, simple formula in a simple linear regression model. And it's this formula. Later in the course, we will look into regression models with more independent variables and more complicated types of regression models. Then that formula would also become a whole lot more complicated and would, for instance, involve things like lots of matrix algebra. I will spare you that, but I will show you how it works in the simple linear regression model, because there it's actually something that's relatively straightforward to actually follow along and do by hand if you were so inclined. So what is the formula? The formula is that the estimated value for B1 for our regression coefficient can be found by, well, taking whatever is coming out at the top of this fraction and dividing it by what is at the bottom of this fraction. And what is at the top of this fraction? Well, there's two elements that we need up for all need to add up for all the individual cases in our data set, for all the cases in our data set, and that's this part xi minus x bar multiplied by this part yi minus y bar, and those two numbers we have to multiply together, and we divide that by the sum of xi minus x bar squared. So you don't need to really know why exactly this formula works. I will tell you anyway, but it's okay if you forget. But I'll tell you what the intuition behind this formula is. If you paid very, very close attention in your previous statistics course, you might recognize this part of the formula up here from a different formula that you have seen before, where this part of the formula up here was divided by n or n minus 1 or n minus 2, depending on which version you saw. And what does that actually represent, that formula then? It is the covariance. It is the formula for the covariance. So if we would take this part of the formula and divide it by the right degrees of freedom, so n minus 1 in this case, then we get the covariance of x and y. And covariance is nothing but a measure that expresses how differences in x go together with differences in y and vice versa. And so how do we express differences? Well, for both variables, we express these differences as deviation scores. So how do changes relative to the mean value of x go together with changes in y relative to the mean value of y. So that is what the covariance represents. And also what you see here at the bottom of this formula might also look familiar to you, because you saw it as part of a formula that we already discussed in last week. It's the top part of the formula for the variance. Again, if we would divide that by the correct degrees of freedom, so n minus 1 in this case, then we could get the formula for the variance. So this is the sum of squared deviation scores. Yeah, divided by the sample size gives us the average squared deviation score, so the average squared distance to the average, or mean squared distance to the mean, which is exactly what the variance is. And because both of these formulas would be divided by the same degrees of freedom, so in this case n minus 1, we can actually forget about that part of dividing by degrees of freedom, because that would give us the same result as just taking the top part of those formulas. So what this actually tells you is that the formula for finding the regression coefficient is actually taking the covariance of x and y and dividing it by the variance in x. Now, why is that? Well, the covariance gives us some idea about the relationship between x and y. It tells us how changes in x go together with changes in y relative to the mean values. But of course, that's on a really, really weird, non-interpretable scale, because that completely depends on the scales of the variables themselves. So we want to somehow also be able to translate this into a relationship that we can actually capture in a as precise a straight line. So to do that, we somehow need to give it a scale, to scale it to something, and we do that by dividing it by a number that captures the scale on which we want to place this covariance. In this case, the scale that we're using is the variance in our independent variable, so basically the x-axis in our scatter plot, because that will give us a scale that then really shows us exactly how changes in what the regression coefficient should look like to represent the right amount of change for each step. Yeah, so we are scaling to the variance in our independent variable. Of course, we also need to know where to locate it on the y-axis, and for that we need to have the constant value, the b0 value, because that will tell us where that regression line intersects with our y-axis. And also for this, there's a relatively straightforward, simple formula. So y bar minus b1 times x bar, which means we take the mean value on our dependent variable and subtract from that the regression coefficient that we just estimated, so just found with this formula, multiplied by the mean value of the independent variable. And you don't need to know why that works, but it's just a mathematical trick that you can intuitively interpret as, once we know the steepness of the regression line, we just basically follow that regression line back to where that regression line intersects with the y-axis. So this is the place where the x-axis gets the value 0, and this is the mathematical formula that does exactly that, basically just tracing back the regression line until we hit the y-axis. That's the reason why that works. So there's a couple of people that we have to thank for this. It's not exactly a new method. It's actually a very old method, and we will be able to tell just how old it is from these two pictures that I'm showing you, because these are the two most famous, commonly used names associated with inventing this method: Carl Friedrich Gauss and Francis Galton. And both of them, along with a couple of other people, have been really the persons behind figuring out the mathematics of how to make this work, and getting it to work in such a way that we actually can find regression lines. So Carl Friedrich Gauss is that dude that gave the normal distribution, also its other name, the Gaussian distribution. Yeah. So how does it actually work? Well, let's apply it in a concrete example. So here I took, again, a hypothetical random sample of 5 students from the PSRM2 course. Again, I made these numbers up. That's not a real sample, but it's just a hypothetical sample that we can use as a nice example. And it's thankfully a very small sample, so we can still follow the calculations along. So we have 5 students. We have student 1, student 2, student 3, 4, and 5. And we have an observed grade for each student on the exam for PSRM2. Yeah, so 8, 4, 6, 2, and 7. And let's say that I have, during the course, sent out a questionnaire survey to all the students. And for this sample of 5 students, they actually filled in a questionnaire survey. And in that questionnaire survey, I asked them somehow about their motivation for the course. So maybe I had a nice question about how motivated are you to work on this course on a scale from 1, absolutely not, to 10, absolutely, I'm super motivated. And then these 5 students actually gave me an answer. So now I have a sample of 5 students for which I also know how motivated they were on a scale from 1 to 10, where more indicates more, a higher value indicates more motivation. And I might do that because maybe I have a theory that more motivated students also get higher grades. Well, that's a nice theory, seems to make sense. But of course the question is, does it actually work that way? So can we try to falsify the theory? Can we try to test the theory by looking at the actual data? So I might not want to use this random sample of students to test that the hypothesis that the more motivated students are, the higher their grades are. And I can do that with a regression model, and I can actually work this out by hand, what that regression model looks like. So because we know, well, we have a formula that we can solve to find the estimated value for B1, our regression coefficient that tells us what the slope is of the relationship between motivation and grade. And we just saw this formula, so we can look at, well, what do we need for this formula? We need xi, we need yi, we need x bar, we need y bar, and that's it basically. So xy we have, that's these values, 9, 1, 5, 6, and 8. I we also have, it's 8, 4, 6, 2, and 7. So we need to calculate the mean values on x and the mean values on y. And then once we have those, we can calculate the top part of this fraction, so basically the covariance of x and y, and the bottom part of this fraction, the sum of squared deviation scores on the x variable, so basically the variance that we have down there. So first step, calculate the mean values. So for grade, that works out to 5.4. Why? Well, 8 plus 4 plus 6 plus 2 plus 7 divided by 5, that's 5.4. And we could do the same thing for motivation. For x variable, 9 plus 1 plus 5 plus 6 plus 8 divided by 5 works out to 5.8. So we already know that this is supposed to be 5.8. Here is also supposed to be 5.8. This is supposed to be 5.4. So now we can use that to work out, well, first the deviation scores on our x variable on motivation. So I can do this for each student. So yeah, the motivation for the first student was measured to be 9. The average on motivation in this entire sample of 5 students is 5.8. So 5.8. So this is a relatively highly motivated student in this group of a sample of 5 students. And you can see this if you calculate the deviation score. So 9 minus 5.8 works out to 3.2. So for this student, the level of motivation was 3.2 points above the average level of motivation in the in this sample of 5 students. For the second student, that's 1. That's really, really low motivation. Minus the average motivation, 5.8, which works out to minus 4.8. So for this student, the level of motivation was 4.8 points below the average motivation in the sample of 5 students. And we also need the deviation scores on Y, on the grade variable. This is, I'm assuming that we are using the Dutch grading system here. So this is also on a scale from 1 to 10, where the higher the value is, the higher the grade is that the student got. And here we see that, well, the first student has a deviation score for that of 2.6. Again, why is that? Well, the observed grade for that student was 8.8. The average grade in the sample of students was 5.4. So 8 minus 5.4 works out 2.6. So this student scored 2.6 points above the average grade on the exam. And again, we can do this for all the different students. And again, we see some people have an above average grade, so that's the positive values, and some people have a below average grade, that's the negative values. So once we have those, we can work out, well, this part on top of the formula, because we need to multiply these two values with each other. So what is xi minus x bar times yi minus y bar? Well, again, you see question mark, pause, think for yourself first, and then hit play again to see what the answer is. So you force yourself to actively think about this stuff, and hopefully you will have worked out that yes, it is 8.32. Why is it 8.32? Well, the deviation score on x, 3.2, multiplied by the deviation score on y, 2.6, that works out to 8.32. Okay, so that's the deviation score. We can do this for all the different multiplied, the two deviation scores multiplied, and we can do this for all the different students, and then we get this multiplied deviation score of x and y for each student. So now we have all those individual values. We still need to add them all up for all the individual students across the entire sample, indicated by the summation sign here. So we just calculate the sum of that. So 8.32 plus 6.72 plus minus 0.48 plus minus 0.68 plus 3.52, and that works out to a value of 17.4. Great, so now we already know what the value is on top of this fraction over here. It's 17.4. What we still need is the bottom of this fraction, the lower part over here. And how do we do that? Well, xi minus x bar squared. So the squared deviation scores for x, we need to find them, and then we need them all, add them all up. We already have calculated deviation scores. They are in this column for x. So what do? We get the squared deviation scores, which is just squaring these numbers, so multiplying them by themselves. So 3.2 times 3.2 works out to 10.24. Minus 4.8 times minus 4.8 works out to 23.04. Again, minus times minus results in plus, results in a positive number, which is exactly why we're doing that. So we're getting rid of the negative numbers, so translating this into a squared scale of only positive numbers. And again, we can do this for all the individual students. We get the squared deviation scores on motivation for all the individual students, and then we need to take the sum of that as well, because that is what's asked of us on the bottom of that fraction, and that works out to 38.8. So now we can actually see that we can solve this formula for B1. It's 17.4 divided by 38.8. That is going to be the estimate for our regression coefficient B1, which works out to 0.448454. And I'm trying to work as much as possible with unrounded numbers, so we don't get too many rounding discrepancies. Yeah, that's the number that we are that we get here. So again, how do we interpret this? Well, that means that in our sample we see that for every additional point on motivation that students score, because it's measured on a point scale from 1 to 10. So for every additional point on motivation, the predicted grade increases by 0.448454 points, again on a scale from 1 to 10 points. This is how much the predicted grade changes depending on different levels of motivation. So that's a positive number that we get. So this indicates a positive relationship between motivation and grade. More motivation leads to a higher predicted grade, or in other words, to a higher mean average grade. Of course, we still need to find B0 as well, the constant in that regression equation, so we know how it is located relative to the y-axis, to the values of grades in this case. So I showed you already what the formula is for that. Now we just need to fill in the numbers. So the constant or the intercept B0 is the average on the dependent variable, so the average grade y bar minus B1, the coefficient that we just found to be 0.448454, times the average on x, the average on motivation that we already have here as well. So this is just a matter of filling in the formula, 5.4, the average grade, minus the regression coefficient 0.448454 times the average on motivation 5.8, and that works out to 2.798969. Okay, great. It's very, very useful to see what exactly is happening here. And like I said, later in the course, it will help you to interpret some of the more advanced issues that we have with regression analysis more easily. But it also shows you something else, and that is that although you might sometimes curse SPSS, honestly, I often curse SPSS because sometimes it's really not very intuitive. It's not always super user-friendly. It takes a lot of getting used to. But we can also be very, very happy that we have something like SPSS, because it just does this for us instead of us having to do that by hand, like people like Francis Galton and Carl Friedrich Gauss used to have to do in the olden days before we had computers or calculators. Yeah, so that's actually, if you look at it that way, SPSS is actually really, really nice and cool, because it helps us to do this stuff very, very quickly. But if you want to be sure, and I would definitely recommend you do that, just open SPSS, create a new data set, and then just enter in two variables, grade and motivation, and enter these 5 values accordingly as they are listed here, and then let SPSS run the regression model, so estimate the regression model for you. And hopefully you will find that the values that SPSS gives you for B1 and B0 for the constant and the coefficient of motivation are exactly identical to the ones that we are calculating by hand here. So if the world ever goes completely down the drain and our computers stop working, we can still solve regression models in our case manually. What a way! What a thing to look forward to, right? So that's the estimate of the regression model itself, B1 and B0. But of course, that's just a sample. So now we know that in our sample there is a positive relationship between motivation and grade. But yeah, probably we don't want to know just about the sample. We actually want to say something about the underlying population. So in this case, maybe the population of all students in that course. Yeah, I just have a sample of 5 students, but there might be, as there are this year, 183 actual students in that course that represent the underlying population. So that means I want to also test this coefficient statistically. I want to understand to what extent can we generalize from this specific sample to the underlying population. And yeah, hopefully you know by now that, well, how do we do that in inferential statistics? Well, for instance, we do that by testing a null hypothesis about the coefficient. And in this case, the null hypothesis that makes most sense would be the null hypothesis that in the population of students, there is no association whatsoever between motivation and grade. So formally expressed, under the null hypothesis, we would expect that the coefficient for this regression equation, if we would estimate that on the entire population, so using all the students in to get the right values for a regression model, instead of a sample of just 5, then the assumption would be that then we would get the regression coefficient of with a value of 0. That in that case, B1 would take exactly the value 0, because that's the situation where there is exactly no association whatsoever between motivation and grade. And then we can test that null hypothesis. Yeah, remember, null hypothesis is always a statement about the population. And we can see, well, how likely is it that we find what we find in our sample if that null hypothesis is in fact true, and expressed usually by the p-value. So the p-value that tells us something about, well, how likely is it to find what we find in our sample if we assume that the null hypothesis about the population is in fact correct. And if we can say, well, that's very, very unlikely that we find what we do find in our sample, then we can say, well, maybe we can reject that null hypothesis in favor of an alternative hypothesis. In this case, the alternative hypothesis that there is in fact a positive effect of motivation on the grade in the population of students. To do that, we need to first get a t-value, because testing regression coefficients means that we need to know what sampling distribution they would hypothetically follow if the null hypothesis is true. And that sampling distribution is described by the relevant t-distribution, the t-distribution for the given degrees of freedom. Degrees of freedom is something I will come back to in one of the next lectures for this test, but for now it suffices the idea that we need the t-value, so then we can use the t-distribution to see, well, how far out in the tail of the t-distribution are we with what we find in our sample. So we can assign a probability to that under the assumption that the null hypothesis is true. And how do we get the t-value? Well, we take our estimated coefficient b1, which we just found, and we divide that by the standard error, the estimate of the standard error for that coefficient. Yeah, so basically looking at, well, what is the signal we are getting about the relationship between motivation and grade, and what is the amount of noise around that signal which is captured by the standard error. So, but before we can get the t-value, we are going to need the standard error, and also for that we can use a version of the OORLS method to estimate the standard error. And again, here for a simple linear regression model, it's a relatively straightforward formula. It's taking the residual sum of squares, SSR, dividing that by the n minus 2, and the resulting value of that, we take the square root of that, and we divide that by the square root of the sum of squared deviation scores in our independent variable. So it's, there is squares and square roots and fractions, but it's still a somewhat manageable formula, even if you're not super strong in mathematics. Some of the elements in this formula we already know. So for instance, we already know that our sample size is 5. So we know that where we have n here, we can just put the value 5. We also know already what the sum of squared deviation scores relative to our mean value on x on motivation are, because we just calculated it. We needed it already to find the regression coefficient, and it turned out to be 38.8. So we already know that. So a lot of this formula we can already fill in, but we still need the residual sum of squares. So the SSR, we still need to find the value for that. So how do we do that? Well, we already saw what the formula is for calculating the residual sum of square. And it's basically looking at what is for each case the difference between what you observe on the dependent variable, in this case grade, and what we would predict based on the model for that specific case on the dependent variable. So again, these are probabilistic models, so we allow there to be a difference between what we predict on the dependent variable, what we actually observe on the dependent variable. And if we talk about the model estimate in the sample, we're talking about the residuals when we talk about the difference of that. And the sum of squared residuals is the idea that we are first going to square the values of these residuals, because otherwise the positives and negatives perfectly cancel out. So we first square them, and then we sum them all up for our entire sample, and then we get the sum of squared residuals. For which this formula we already know for each case what the observed value is, because that's just the grade that each student got. But we still need to calculate what the predicted grade is, because we first need to estimate our regression model to actually be able to make those predictions. Now we have estimated the regression model, we know what the value for B0 and B1 is, so now we can calculate the predicted value for each student, and if we have both of those numbers, then we can look at what is the difference. That's the residual, and that we can then square and sum together, and then we get the residual sum of squares. So I'm starting a new table here because otherwise the table would get a little bit too massive, but I kept the same students, the same grades and the same motivation. And now we're going to step by step calculate our standard error. So the first thing we need is we need the predicted value on the dependent variable for each student. So the predicted grade based on the level of motivation that we have observed for each student. So again, question mark, pause and think. How in general would we calculate that predicted value? Yes, indeed, it is based on B0 and B1, which we have found to be, for B0 the constant, the value 2.798969, plus the B1 value 0.448454 that we just found, multiplied by the value on the independent variable motivation, in this case for each student, and that's going to give us the predicted value for each student. So for instance, the predicted value for the first student, so y hat for student 1, what would that be? Yes, great, well done. It would be just filling in that formula for the first student. So it's 2.798969 plus 0.448454 multiplied by the value of x for our first student, for our student 1. And we know what that value is supposed to be. It's supposed to be 8. This is it's supposed to be 9 because this is the observed level of motivation for the first student. So that works out to 2.798969 plus 0.448454 times 9, the observed value on motivation, which works out to 6.835055. So we now know what number to put there for the first student for the predicted value. So you see that in this case the student was predicted to score a grade of 6.835055. That was the predicted grade on that student, not the actual observed grade, just the predicted grade based on our model. And again, we can do that for the second student. Did you figure it out? Yes, great. It's again just run through the formula. So in this case, the observed level of motivation was 1. So you just calculate 2.798969 plus 0.448454 times 1, which is just, of course, multiplied by 1 is just the same number. So we get 2.798969 plus 0.448454, our regression coefficient, and that works out to 3.247423. So that's the predicted grade for the second student. So quite a bit lower than the first student, which is logical because the motivation was quite a bit lower for that second student. So the predicted grade is also going to be lower because we found a positive relationship between motivation and grade. And again, we can do that for all the individual students. We can calculate the predicted value. And now we have a predicted value for each one of those students. Great. Of course, now we need to actually get the residual value, which is the difference between the predicted value and the observed value on the grade. So again, pause and think. What would be, how would you calculate the residual for the first student? Residual being the difference between predicted and observed. Yes, it's 1.164945. Yeah, so it's 8 minus 6.835055, so the observed minus predicted, and you get the residual, so in this case 1.164945. So in this case, this student actually got a higher grade than we would have predicted based on our model. Based on our model, we would have predicted that with a motivation of 9, the student would be predicted to have a grade of about 6.8. And actually the observed grade was actually an 8. And that's 1.16 points roundabout higher than that. So this student basically exceeded the expectations that we have based on the level of motivation alone. So for the second student, you see it's also the actual grade was actually a little bit higher than the predicted grade. Still quite low, but hey, that's not surprising if your motivation is at 1. So for that student, the residual was 0.752577. Yeah, again, the observed grade of 4 minus the predicted grade of 3.247423 works out to this residual of around about 0.75. And again, we can do that for all the different students. You see here we get positive numbers and negative numbers. So the positive numbers indicate the students where the observed grade was actually higher than predicted. The negative numbers represent the students where the observed grade was actually lower than predicted based on motivation alone. So once we have that, we can then find, could say, well, look at the sum of that. We don't actually need that, but I put it in here anyway, just to make you think, what is going to be the sum of these residuals? And hopefully you haven't reached for your calculator or furiously started writing down the numbers, but figured that it's going to be 0. Because that's exactly what the residuals sum to if we use this way of finding the regression line. Then the sum of these residuals are going to turn out to be exactly 0, because that's exactly how that regression equation, this estimation procedure for the regression equation is defined. So we want actually the squared sum of residuals, so we get some positive number that we can that we basically have that we can work with. So in this case, we just take the squares of these residuals for each case. Yeah, so for each individual case, we look at the residuals and we take the squared of that, so multiplying the value of the residual with itself, and then we take the sum of all of those, and that will give us the residual sum of squares. So for the first student, how would you calculate the squared value of the residual? Yes, it's 1.164945 times 1.164945. So the value of the residual multiplied by itself, and that works out to 1.3570968. And here I definitely started rounding at some point, but roundabout. And you can do the same thing for the second student. How would you calculate that? Well, yes, 0.752577 times 0.752577, which works out to 0.5663714. And again, we can do this for all the different observed residuals in our sample data set. And once we have all of those, we can calculate the sum of all these squared residuals, the residual sum of squares, which works out to be 15.396907. So now we know the residual sum of squares, which is about 15.4 roundabout. So now, finally, we can calculate our estimated standard error, because now we have all the ingredients that are in that formula for our estimate of the standard error, because now we also know SSR. So filling it in again, we now know what we have to do is we need to take the residual sum of squares, so the sum of square of the residuals, 15.396907 divided by the sample size 5 minus 2, and we take the square root of that and we divide it by the square root of 38.8, and that works out to roundabout 0.3637. So this is now our estimate of the standard error. So now we know two things. We know the estimated coefficient for the effect of motivation based on our specific sample. Now, our sample of 5 students, and that turned out to be a coefficient of 0.448454. That was just a sample. We want to also say something about, well, how reliable is this coefficient in representing the true population coefficient? So the how well is this likely to reflect what the regression coefficient would be if we would have used all the students, so the entire population, to calculate this regression model. So by getting the standard error, we learn about, well, how much would the regression coefficients that we would estimate if we would take every possible sample from the population of all students, and for each of those possible samples estimate such a regression coefficient. How much would all those individual regression coefficients vary around that true population coefficient that we cannot actually observe? Because that is what the standard error tells us. It gives us based on our sample, an estimate of how much variation we would expect around the true regression coefficient in the population in each individual sample that we could have taken, and we have taken just one of those samples, of course, but at least now we have also an estimate on what would be the most likely variability of all sample regression coefficients, because if there's a lot of variability, then it's a not very reliable estimate of the true population regression coefficient. If there's not so much variability between the individual regression coefficients from the different possible samples, then it's a more reliable estimate of the true population regression coefficient. So in other words, what a standard error really is, it is an estimate of dispersion of the sampling distribution. So how spread out the sampling distribution is around the true population regression coefficient. And it is not the true actual dispersion of the sampling distribution, because we cannot observe that. That would imply being able to take all possible samples. That would basically imply that we already have the entire population observed. We don't. We only have one sample. So it is an estimate, but it's an estimate of the standard error. But what it tells us is basically how dispersed is that sampling distribution. If all the individual regression coefficients that we could get from all possible samples are very, very close together, we get a small standard error. And that also means that each individual regression coefficient is quite likely to be quite close to the value of the true population coefficient. Whereas as the standard error is very, very large, then this tells us that, basically the individual regression coefficients that we could get from taking all possible samples are basically all over the place around the true population coefficient. So then we know that each individual regression coefficient is probably somewhat less likely to be a good reflection of the true population regression coefficient. So that's really what the standard error tells us. And this is also why the most fundamental things to get right in a regression model is the coefficient. In this case, we're talking about the unstandardized coefficients, so the B coefficients, and the standard errors that belong to those coefficients, because they tell us, these two things tell us about what is the observed as a relationship in our sample, and how uncertain do we need to be about how that reflects the true population relationship that we are actually interested in. So that's why always coefficient standard errors are the most fundamental thing to get right in the regression models, and everything else follows from that, basically. So let's look at this standard error in a little bit more detail, because like I said in one of the previous lectures, I know that these formulas are a bit, take some getting used to, take some time to know how to read them, but they're also helpful because sometimes they show us also some properties that would not maybe be obvious if we wouldn't have the formula, and that can be useful to be aware of. So if we look at this formula, one of the things that you can tell from this formula is because we have the residual sum of squares on top of that fraction, so that's basically the value we start out with. That also implies that the value we will get for the standard error will be larger the larger the residual sum of square is. And what does the residual sum of square tell us? Well, it tells us basically how spread out all our individual observations are around our regression line. So a very well-fitting regression model will have a relatively small residual sum of squares, and a relatively badly fitting regression model will have a relatively large residual sum of squares. So basically, it expresses the dispersion around our regression line. And well, if you think about it like that, it actually makes sense, right? If you have a regression line and all the individual observations are really, really close to that regression line, so the residuals are very, very small, then that model does a very, very good job of predicting your dependent variable. So you get a lot of confidence about the effects that you find in that in that model, so the coefficients that you find in that model. Whereas if all the individual observations are very, very spread out around that regression line, then that suggests that there is a lot more variability going on that you haven't captured with your regression model. So you become a lot less certain about how well your regression coefficient actually reflects the true population coefficient. So the standard error increases the more spread out the individual observations are around the regression line, because then we have a regression model that does a relatively less good job of predicting the outcome. So we are relatively less confident that this is actually a good reflection of the true population regression coefficients. So that's one thing you can learn from that. The other thing you can learn from that, well, notice that we divide the residual sum of squares that we start out with by the sample size, -1 in this, -2 in this case, but by the sample size basically, which means that the value we start out with, SSR, gets divided by a number that is directly related to the sample size. And the larger the sample size is, the larger is the number we are dividing SSR by. So the more we increase our sample size, the larger our sample size is, the more observations we have, the larger is the number we will divide SSR by, which means that it is going to, the larger the sample size is, the smaller the number on top of this fraction is going to be. Yeah. So what does that tell us? It tells us that as the sample size goes up, the value of the standard error goes down. So the larger our sample is, keeping everything else the same, the larger our sample is, the smaller the value of our standard error. And also that, if you think about that, makes sense, because what that means is, well, the larger our sample, the more confident we become that our sample regression coefficient will be relatively close to the population regression coefficient. And the smaller the sample is, the less confident we are that our sample regression coefficient is close to the population regression coefficient. Yeah, because then we have a much wider sampling distribution, because we have a relatively lower amount of observations. So more observations mean more reliability in that sense. And of course, a standard error should capture that. So the standard error basically captures these things that go into uncertainty when we talk about a regression coefficient representing the true population regression coefficient. And two things that go into that is the dispersion around the regression line, so how badly our model fits with respect to that specific variable. And then another thing that goes into that is the sample size. The larger our sample size is, the more confident we become. So the less uncertainty we have. Yeah, so those are just two things that you can learn from these formulas that also, I think, make a great deal of intuitive sense. And it tells you also something about why that standard error is such a useful number to be looking at and trying to estimate that correctly, because it tells you a lot about your level of uncertainty, and so by implication the generalizability of your regression coefficient as representing the true population regression coefficient. Of course, then we can use that standard error to actually test our regression coefficient, and for that we need to use it to calculate our t-value, so we can compare that to the theoretical t-distribution. That t-distribution, you can thank William Seeley Gossett for that, and there's a reason it's sometimes referred to as the student's t-distribution, because William Gossett was working as an kind of agricultural researcher at the Guinness factory. So we're talking about the beer Guinness, and he was trying to compare yields of different types of ways of planting fields to get to harvest the stuff you need to brew beers, so he was really a technical person working in a private company, but also a bit of a nerd and a scientist. And so he found out that normal distributions sometimes don't work so well, but there is a different type of distribution that does really work well to use as a theoretical sampling distribution, and that is what he called the t-distribution. And he published that, but he didn't want to publish it under his own name. That was a little bit not done back then for given his position. So he published this anonymously as student. So that's the reason why the t-distribution is sometimes called the student's t-distribution. So we get our t-values by taking our estimated coefficient and dividing it by our estimated standard error. Again, our standard error is an expression of the sampling distribution, but that's on a scale that we basically don't really know how to interpret, because that's basically on the scale of it's related to the scale of our specific variable and the underlying variances of that. So we need to somehow translate this into a scale that we actually can work with, that we know what exactly the distribution looks like. So what we're doing here is basically translating our ratio of coefficient to standard error that basically translates that into the t-distribution, and the t-distribution is a known distribution, so we can exactly mathematically describe the curve of that distribution. So we can exactly see, well, how far is the t-value that we have, how far in the tail of that t-distribution is it located, under the assumption that the null hypothesis is true, because the null hypothesis has the function of pinning down the center of that hypothetical sampling distribution. Yeah, so the top of that distribution is basically where our null hypothesis is located. So again here, the formula tells you something interesting, and notice that a larger coefficient also means that for the same standard error we get a larger t-value. Again, intuitively that makes sense. A larger coefficient means that we have a larger effect, that the predicted value on y increases faster with the steps on the scale of x. So the larger our coefficient is, basically the stronger the signal is that we are getting about the effect from our data. Very, very large coefficients indicate that there might be very, very strong effect. But of course, we need to also take into account, well, the uncertainty around that effect. And here you see, well, we're dividing the coefficient by the standard error. So the larger the value of the standard error is, the lower the absolute value of our t-value will be. Again, that makes sense. The larger your standard error is, the less certain you are, the more noise you have around your regression coefficient. So larger coefficient means higher t-value, so more likely to find a low p-value. Larger standard error means lower t-value, so less likely to find a low p-value. Yeah, those are of course then related to each other. And so, I said, well, we're going to talk about the degrees of freedom for this test. It is actually defined for regression models in general as n minus k minus 1. So n stands for the sample size, k stands for the number of independent variables in your model, and the minus 1 is because we're also estimating a B0 coefficient, a constant. Again, you don't need to worry on a fundamental level about what degrees of freedom exactly means, but just know that we have different t-distributions depending on what the degrees of freedom are. So the degrees of freedom defines what t-distribution exactly we need to look at if we want to do this test for our data. And so you have to remember that the t-distribution looks a lot like the normal distribution. It's just that it's more spread out. It has a little bit, the tails are just fatter, indicating basically that we have a more spread out sampling distribution than a normal distribution would be. But you also have to remember that the larger your sample size is, the more the t-distribution looks like the normal distribution. So the larger your sample size is, the more observations you have, the smaller is going to be the difference between the t-distribution and the corresponding normal distribution. So why am I telling you this? Because there is a useful trick you can learn from these pieces of knowledge, because that means that whenever you see a research published somewhere and they are not giving you p-values and they are not giving you asterisks to indicate statistical significance or whatever, and you need to, let's say, which sometimes happens, and you need a kind of rough way to say something about where are we in terms of p-value statistical significance. Well, if the sample size that is being used is large, and if we assume that we would be working with this alpha, the significance level of 0.05 on a two-sided t-test, then roughly speaking, we could say, well, the effect is significant if the coefficient is at least twice the value of the standard error. Why at least twice? Well, because if it's large sample, then we can basically think of the ratio of coefficient to standard error to follow a normal distribution, because then the t-distribution and normal distribution look just about the same. And for the normal distribution, we know exactly what the different values would be on that distribution and the associated probability values, associated p-values. And so we know, for instance, that the 95% confidence interval, which is equivalent to working with an alpha of 0.05, would be indicated by minus 1.96 roundabout up to positive 1.96 on the normal distribution. So the values on the normal distribution, so the z values, between minus 1.96 and plus 1.96 roundabout. Those give you the 95% confidence interval. So in other words, if you find a coefficient that's roughly, so 1.96, let's just round that to 2. If your coefficient is twice the size of the standard error or larger, then roughly speaking, we are talking about, that it's a significant effect. If we would just say significance is set at alpha is 0.05 and we're assuming a two-tailed test. This can sometimes come in useful if you need to read tables and people don't present you all the information because you assume that you know how to interpret this. So that's a useful trick. Now, goodness of fit, also something we talked about in the A lecture, and I showed you the F ratio. So this idea that you can use an F test to test the goodness of fit in your model, specifically test the null hypothesis that your R-square value is 0 in the population against the alternative hypothesis that is larger in the population. So you already saw this formula where we're taking the mean sum of square of the models and divide them by the mean sum of square of the residual, and then we get the F value, the F test statistic that we can then use to find a corresponding p-value, probability value. Now, what does this F ratio represent? Well, you could say very, very roughly what it represents is a ratio of how good the model fits the data relative to how bad the model fits the data. So the sum of square of the models, for which the mean is on top of that fraction, indicates basically, well, how much better did my predictions become in this model compared to just using the mean as a prediction for my dependent variable, and the sum of square of the residuals, so for which again we take the mean sum of squares residuals on the bottom of that fraction, tell you about, well, how what is the part of the variation in my dependent variable that I'm not able to explain with my model. So basically it is a ratio of how good the model fits relative to how bad the model fits. Now there is a different way that is mathematically equivalent for writing this this formula for the F value. So both of these ways of writing it give you exactly the same result. It's just that it's a different way of presenting the formula. And this is that formula. So n minus k minus 1, so some degrees of freedom thing happening there between the brackets, times the R-square value divided by k, again some degrees of freedom thing happening there, multiplied by 1 minus the R-square. And you can forget about the n minus k minus 1 and the k for now. That has something to do with degrees of freedom. Just focus on the R square and 1 minus R square part of that formula. Because you already know what the interpretation is of R square. It's the proportion of explained variance in our sample. So it tells us how much of the variation, expressed as variance, so differences between the cases that we started out with, could we explain away with the independent variable that we included in our model. So in the example that we just used, how much of the variance in grades can we explain with differences in motivation? So that's then a proportion from 0 to 1, indicating the proportion of explained variance in the of the model in our sample. And multiplied by 100, you get a percentage of explained variance. So R square explained variance. Well, if R square is explained variance, then what is 1 minus R square? It's the unexplained variance. It is the variance that is left. Again, R square is a proportion. So it runs from 0 to 1, and it tells you what is the proportion of explained variance. Then whatever variance is left, that's the unexplained variance. So 1 minus R square is the unexplained variance. So what we have on top of this fraction is some thing related to the explained variance. And what we have at the bottom of this fraction is something related to the unexplained variance. And that maybe makes it a little bit easier to understand why we can roughly interpret this F value, this F ratio, as a ratio of how good does the model fit, and so R square, relative to how bad it fits. So 1 minus R square, the unexplained variance. So this is in that sense, it's useful because it gives you a little bit more of a hopefully intuitive understanding, but also later we'll see in the course that we can extend this formula even further and do even more interesting statistical testing with it. So also in that respect, it's good that you already know that we can rewrite the same formula in a different way and then we get this formula instead of this formula, but it's mathematically it's exactly the same, gives you the same result. Yeah. So we talked also about, well, what are we testing with this f value? And we said, well, we are formally testing the null hypothesis that r square is 0 against the alternative hypothesis that r square is larger than 0. Again, remember, null hypothesis always a statement about the population. Yeah, so what can we do? We assume that is the case in our population, and then we test that, and then we can't prove it, but we can maybe reject it in favor of some alternative hypothesis about what is going on in the population. So these are statements about what is going on in the population, and we try to test them, test the null hypothesis using our sample, and then maybe we can reject the null hypothesis, and that then gives us support for the alternative hypothesis. So in this case, what does the null hypothesis mean? R square is 0 in the population. That basically is the assumption that our estimated model, if we would have used the entire population to get the values for that model, then we wouldn't have been able to explain any differences at all in our dependent variable. Yeah, so again, translating that to the example of grades and motivation in our sample. So if we would calculate the R square value based on that sample, then we can use the f-test to test the null hypothesis that in the entire population of students, differences in motivation, because that is what was included in our model, differences in motivation explain no variation whatsoever in the grade. So there is nothing in the variance of the grade that we can explain with differences, variance in motivation. Yeah, and then that's of course a useful null hypothesis that to be able to reject, because if we can reject that null hypothesis, then that would support the alternative hypothesis that R square is larger than 0. So it takes a positive value in the population, which means that our model would explain some of the variance in the population, would explain some of the variance in the grades in the entire population of students. Yeah, so that would be, of course, yeah, an indication that we are at least able to have, that we at least able to explain some of those differences in grades with the model that we just estimated in our sample. Yeah, so that's what we are formally testing when we are testing this null hypothesis with this f-test. Yeah, so the goodness of fit of the entire model. In this case, the entire model basically consisted of one independent variable, motivation. Yeah, that's a simple linear regression model. We just have one independent variable. And so we test whether we would explain any variation at all in the population if we would have the entire population or none whatsoever. Notice again, the alternative hypothesis here is directed. So we under the alternative hypothesis, we would assume that R square is a positive number. It's larger than 0. And again, that can only be a directed alternative hypothesis that indicates that R square is larger than 0, because we cannot ever explain less than nothing. Yeah, so variances can't be smaller than 0. So we can't ever explain less than not explaining anything at all. So it's always going to be a 0 or a positive number, R square. So that's the null hypothesis that we would formally be testing with this f-test. However, if we have a simple linear regression model, we only have one independent variable in our model. And that has an implication. That has the implication that the f-test that we are using here to test a null hypothesis about the R square value at the same time also tests a null hypothesis about our regression coefficient. And specifically it tests the null hypothesis that that regression coefficient is also 0 in the population against the alternative hypothesis that it is not 0. So that's an undirected alternative hypothesis. Could be positive, could be negative, but not 0. Yeah. That seems weird. We have one statistical test that actually tests two different things, and one of those things, the regression coefficient, we just used a different test, the t-test, to test this with. And now, yeah, I'm telling you that, yeah, actually, that would give you the same result as the f-test. And you can actually, maybe you've already seen that when you did the assignment, that the p-value for the f-test is the same as the p-value for the t-test for the regression coefficient. That's not coincidence. And I think if you think about this, well, if you have a simple linear regression model, then, well, what did we do? We used one independent variable to explain differences in the outcome variable in our dependent variable, to explain variation in our dependent variable. And we also said, well, goodness of fit is always about comparing the simple linear regression model to an even simpler model, which is just using the mean as a prediction. Yeah, so if we test that R square is 0 in the population, what we're actually testing is, does our regression model with the independent variable included fit the data better that we observe, significantly better, so to such a degree that the model fit improved so much that we say, well, it's unlikely to see so much improvement in R square if in the population we would be able to explain no variation whatsoever. So it actually does this model that we just estimated, this simple linear regression model with an independent variable, does it fit the data significantly better than the most simple model we can think of, which is just using the mean B0 as a prediction for our dependent variable. But because of the only difference between this model and this model is that we have included our independent variable, that we have a coefficient estimated for that independent variable. So in this case, if we say, well, this model has a better goodness of fit than this model, the implication is also, well, what is the difference between those two models? Well, it is that regression coefficient for that independent variable. So what is the difference? It is that regression coefficient. So if this model, this simple linear regression model, is significantly better than this model, then that also means, well, that has to be because the effect is significant. Yeah, so these two things are completely equivalent in the simple linear regression model. Again, right now you're probably a little bit annoyed because you're thinking, well, if all these tests do more or less the same thing, why do you show them? Show us all of them? Why do we need to know this? Why make it so complicated when it all does the same thing? Well, as always, later in the course you will find out why, because later in the course we can use this knowledge to test more elaborate and more complicated, but also much more interesting hypothesis. Yeah. So basically what we can tell from this is there's just one independent variable in our model. So if we have a simple linear regression model, then testing whether the explained variance of the model is significant is basically the same thing as testing whether our coefficient for our independent variable is significant. Comes down to the same thing, so you also get exactly the same p-value for that test. Yeah, so that's good to already know. Yeah, and then I want to talk a little bit more about, we already saw now that, well, they have this simple linear regression model where there's an independent variable. We have an even simpler model where you're just using the mean as a prediction, and actually we can write those models out in the same way and actually look quite alike, with the only difference being whether there is a second coefficient, a B1 coefficient, and an independent variable x included or not. So why is that? Well, let's go back all the way to the mean value. Yeah, the mean is a descriptive statistic, and what does it represent? Well, we hope that it actually represents something called the expected value for our variable, whether it's variable y or x. Let's now assume we're talking about a dependent variable, a variable y. Then the mean should represent the expected value. So not the predicted value, the expected value. Well, what is the expected value? There's a very nice mathematical representations of that I could show you, and then you probably would really hate your life unless you really love mathematics. So I'm not going to do that, but I will tell you how you can think of this expected value on an intuitive level. So that expected value on an intuitive level represents what would be my best guess, my best prediction for a value on that variable. And if we're talking about just the expected value without anything else, then we're talking about what would be my best guess for a value on that variable that is for a case that is randomly drawn from the population. So a randomly drawn case, so randomly drawn in this case meaning everybody in the population has the same probability to be included in the sample. So if we randomly draw a case from the population and we don't know anything else, what would be our best prediction, our best guess of the value of the variable that we are looking at for any variable y. Yeah, and yeah, it makes sense to use the mean for that because, well, if these variables probably follow hopefully some kind of a normal distribution, or maybe not perfectly normal, but at least somewhat symmetrical. So the left and the right side look more or less the same, not any kind of weird shapes. Many variables do have those kind of symmetric or more or less symmetric distributions, because usually the extreme values you don't observe them so often, and it's the values in the middle that you do observe the most. So you get this kind of bell-shaped distribution, and whenever you have this kind of bell-shaped distribution, which is more or less symmetrical, so it's not really skewed, it does have one single top peak, which not always the case, but often that is the case, or at least approximately the case, then our mean value is actually a good representation of the expected value. So our best guess for a value of y for a randomly drawn case. If the distribution of the variable is not symmetric, if it's very skewed, or it has a weird shape in other ways, then that might not be the case. Then the mean value might not be a good representation of the expected value. For now, you don't need to worry about that. Later in the course, we'll see what is happening then and how we can deal with that. But if you have these kinds of symmetrically distributed variables, then the mean is a reflection of the expected value. It's a good estimate. It's even what we will later learn is an unbiased estimate of the expected value. But the expected value itself is something that's not observable. It's kind of a thought experiment. If we would draw a random case from the population, what would be our best guess for the value of that case on that variable if we don't know anything else? And well, then the mean value is going to be your best guess, because that's where most of the observations are located, right at the top of that distribution of the variable. So formally, we would say that the expected value, so the E stands for the expected value for our variable y, then is identical to the mean value on our dependent variable y. So the expected value in that case is represented by the mean value of y. And that mean value we can also write as a model. So whether we put down y bar or b0, it's just two different ways to write down the same thing. Remember, if we have a regression model without any independent variables included, then we have just b0, and then b0 is just the mean value, and the residuals are just the deviation scores. Right? So really the mean value is already a type of regression model. As a matter of fact, it's no coincidence that we already saw that OLS, this estimation procedure, works by finding the smallest sum of squared residuals. That's the same way we could theoretically also go about how to find the mean, just the mean value in our data, by making the sum of squared deviation scores the smallest possible value. As a matter of fact, sometimes the arithmetic mean is even referred to as the least squares mean. So really, a mean is already a type of regression model. It is a regression model where we have no independent variables whatsoever. So we just have a b0 value. That is what our mean actually is. So what is a linear regression model then? That's a model where you do have an independent variable in there, and that is the reason why the interpretation then is that our regression equation describes the mean of our dependent variable conditional on, so depending on the value of our independent variable. Which, given that we assume that our mean is a good representation of the expected value, tells us how the expected value on our dependent variable changes as our independent variable changes. So in other words, now we know a little bit more about our cases. We also know the value on the independent variable, so we can have a little bit of an informative best guess for a value on our dependent variable for a randomly drawn case, because now we can also incorporate knowledge of that independent variable. So now we get the regression equation that tells us how that expected value changes as x changes as our independent variable changes. So again, we can write this out formally in the same way. We can say, well, the expected value for y, our dependent variable, conditional on the value of x, our independent variable for each case. So this upright bar here indicates conditional. So that's a fancy word for dependent on that. So the value of y depending on what value we observe for x for our independent variable. So what is a regression model? When does a regression model work well? What does it tell us? And let's assume for now that it does work well. It tells us how the expected value on our dependent variable changes depending on the value on our independent variable. And that's exactly what the regression equation describes. Yeah. So our regression equation is basically nothing more than a more elaborate version of the mean. Yeah, the mean is the unconditional expected value. The unconditional meaning if we have no other information, then what is that value? Conditional meaning now we have other information. We know about x, about the independent variable. Yeah, so then our regression model should represent the expected value on our dependent variable depending on the values on our independent variable. And that is then described by our regression equation b0 plus b1 xi. Yeah, so basically there is no fundamental difference between a mean and a linear regression model. It's just that we are adding more information to the model by making it a linear regression model. So now we have information on an independent variable that gives us a little bit of a better way of guessing a randomly drawn value for a randomly drawn case on our dependent variable. Yeah, if I just know if I only have observed students and I don't know about anything else like motivation, then my best guess, given that it's a random sample, so every student would have the same probability of being included in that student, is just take the average grade. But if I also know about their motivation, I can make a better guess. Then I have a conditional expected value, so I can see, well, based on what their motivation was, what would be the predicted value based on our regression model, and that predicted model should then represent the expected value on our dependent variable on the grade. So the best guess, depending on the observed level of motivation. Yeah, so expected value is something we can't observe. It's a theoretical construct. What would be the best guess for a randomly drawn case? The predicted value is actually something we do observe. Yeah, we just calculated predicted values based on a sample. And so a linear regression equation gives us predicted values, and in doing so tries to describe this hypothetical expected value. You don't need to worry about too much yet about the difference, but later in the course you will see that that's exactly where it can go wrong if the way that the predicted values change do not nicely coincide with the theoretical expected value. But for now, you don't need to worry, but I do want to show you this because sometimes people think that linear regression is some kind of magic thing that all of a sudden we have, and then we get all kinds of statements about causality and blah, blah, blah. It's really just a more elaborate version of taking the mean of a variable. Be aware of that already. I think at some points during this course you will actually sometimes be a little bit disappointed as just to how simple the stuff that we are talking about actually is when you really think about that. Of course, getting there and understanding it is not simple at all. So don't panic if not everything makes immediate sense to you. So I already wanted to show you that this idea that there is really linear regression is just basically one step up from just taking a mean value on a variable. That's it for now. I will be seeing you hopefully in a Zoom session. Take care, hang in there, and be patient in learning this stuff. Sometimes it takes a little bit longer, both the theoretical and the practical side of it. So don't get frustrated too quickly. Ask for help, and then you will be fine. Bye bye.